This is SIGGRAPH at UCI. This is our second meeting during week 4 of fall quarter at UCI. Um, this is a presentation on ray tracing in hopefully the span of 1 hour, just like a little thingamabob. This is supposed to be an in-person workshop, but no one's here, so I'm just gonna record this, and hopefully, someone's interested enough to watch it. But basically, what we have here is we're gonna go over. There's a tutorial online called Ray Tracing in 1 Weekend, and it's about how to make a ray tracer in C++. However, we have an interactive component here that you can use to kind of aid your learning as we're going through the slides. Since it's a Jupyter notebook, it's in Python. I'll include the link maybe in the description or something. So there's that. And you can open it up, and there's going to be some fill in the blanks, and you can look through those as you listen. Yeah. So let's just get started. Basically, what's the reason we would even want to make a ray tracer? The standard graphics pipeline, you're using a vertex shader or fragment shader, and you're gonna make a mesh of some sort and rasterize it. That's all fine and well, but sometimes it doesn't make the most realistic images, and maybe you want something a little more physically accurate, and that's what we use a ray tracer for. This one in particular, all ray tracers in particular, they're basically just objects in a scene and a camera, and we're going to use some projective transformation to get that object into our image plane as shown in this image here. We're going to be sending out rays from the camera and trying to see if they detect an object. The reason for doing this instead of going from the light source to the object into the camera is that not every ray from a light source goes into the camera, and so that'd be a lot of wasted computation. But that's kind of just filler. Let's actually get started. So let me change slides. I kind of explained this already. It's a ray tracer is basically sending rays out into a scene and seeing if it hits anything, right? If an object is hit, we're gonna go look at the information we have for that object and see what color it returns, right? And down here is some of these graphics. Most of them are from the ray tracing book. I will also link that down in the description. But this is basically just a ray, and we have some starting point A, and we have any point along the B or any point along the ray B, and we can get this by just plugging in whatever key value we want into the ray. So it'd be like A plus B times T, right? And that would equal B if T was 1, right, for example. And also, before we even start programming the ray tracer, we want a format for how the image is going to be displayed and written out. And the format we're using is called PPM, or Portable Pixmat format. It's basically just like a text file, as all data files are. We label it here P3, that it's a honestly, I don't know what this means, so let's skip that. But we have an image width and a height here in the second row. And then in the third row, usually for color intensity, we want 256 values. So we're going to go from 0 to 255 inclusive. And then from here on out, each line is basically just a pixel in our image that image resolution that we have here. So, for example, this is the 00 pixel, and or I don't know how it's actually formatted, but it's going to be the top left pixel, that's for sure, right? And we have a R value here of 163, a green value of 200, and a blue value of 255, right? This is gonna be like scan lines, so we're gonna go from, you can see my mouse, we're gonna go like left to right, and then down one row, left to right, down one row, left to right, and that's pretty much it. Here's some code to do this. It's basically just a double for loop where we loop through the height first, and then we loop through the width to go left to right. So yeah, that's basically it. And yeah, the 00 pixel would be the top left, as shown by the loop. We can get an idea of how much like more processing time we have left with a printout statement here, where it shows like how many lines we have left. And for this specifically, it's going to go really fast, so it doesn't really matter. But for some more expensive images, pretty useful. Based on our height and where we are on the width, we're going to have some color values. We're going to make sure they either max out at 255 or are at 0 with these three, because R, G, and B here are some fraction out of the entire like image resolution. Right? I kind of spoiled it by going to the next slide, but I was gonna ask, like, just based on this, what do you think the top left color is going to be? The answer, of course, is black, because we're gonna have just like two 0 values here and a for red and green and a 0 value for blue in the top left. So it's just gonna be 0, 0, 0 in the top left. So we get some black value there, right? And conversely, we get like max illumination in the bottom right corner, right? And since we're only changing the R and B values, it's gonna go from red to green based on width and height. And since we're sending something out in a scene, we're sending rays out from a camera into a scene, we kind of need to model that entire thing. And this is basically our model. We have our camera. Conventionally, usually in like computer graphics and vision, the negative Z axis is into the image plane, or the viewport as we call it. Our up vector is going to be the Y axis, and to the right is going to be the X axis. Sometimes this Y, you'll see it as negative Y too, but we're going to go for Y here. And what this viewport is basically just like a cross section of the like view we're getting, right? So like if you can imagine this camera center, there's going to be like a huge kind of like pyramid or conical shape that's coming out of it, and we're just going to get a cross section. Like I said, this is basically just the slice along the cone projected by the camera. We have a bunch of parameters here. If you're not looking through the collab, I would highly suggest doing so, because these are like pretty useful to fill out the blanks I left in the collab. But basically, we have some delta U, and U is going to be our length vector, and we have some delta V, and our V is going to be our height vector, right? And so obviously we're going to go, iterate with this delta U, and then we're going to iterate height with this delta V. And Pixels are like a square, I guess. Not always, but you can, just for simplicity, we can think of them as a square, and we want to look at the center of the square. So like, for example, if we're looking at this 0, 0 pixel, we're gonna probably do like half of a delta U, right? And then half of a delta V, and then look there, right? And that's our eye of the pixel. Now that we have our camera model, we're gonna just do like a simple background that's gonna go from uh, blue to white, blue on the top to white on the bottom. And this is some code that does this. Um, we're gonna send out a like a view ray from our camera, and we can see in the code here it's just some vector. We're gonna normalize it and make it a unit vector because that's always helpful for math reasons. And you're gonna get the unit direction. We're gonna use kind of like our how much we're looking up as some sort of parameter to color the simple background and like just do linear interpolation. If we think about like the actual like numerical y value of these vectors as we're looking up to down, it's not going to be 1 or like -1 because like it's not looking directly up, which would be 1, not looking directly down, which would be -1. So we're just have something in between 1 and 0, right? So we have something in between 1 and, or we're gonna have something between 1 and -1, but not reaching those endpoints. We're gonna have something there for this y value. We're gonna add 1 to it and then have it. And these vec3s here are actually color values. So we're gonna return some like sort of color value that is modified by this looking up or down parameter, right? And with some basic linear interpolation formula right here. And we're gonna plug the A into it, and it's just gonna return some color, right? Some color in the form of a vector, with 3 dimensions, right? And as shown like kind of back here, we're gonna put, since we're returning this vector, this is a function that's gonna be put into here later on, and we're gonna use that vector and just print it out here into our ppm file, right? And obviously this interpolation formula makes sense because if you're looking like completely in one direction, this are like completely at the end, I guess, right? A is 1, then you're going to get the n value because 1 times n value. And if you're completely at the beginning, you're just going to get the start value, right? But we're never going to get this start value, right? Because we're not looking up or down completely. Actually, that's probably a lie. I might cut that out or not because like, let's say the top of this thing is +1 and the bottom is like 0, right? We are going to get like a 0 because it's just the y like quantity. It doesn't really matter. That it's not a vector that's just straight down here. Like for example, if we have like a line here, this whole y value is the same. So I lied. Sorry about that. But this is the image we get. Yeah, it just goes from blue to like light blue. Okay, so now we want to put something in this image. This is kind of the interesting part. So we're going to put a sphere in there. This is the formula for a sphere. If you've done some like high school math before, you've probably done this with without z, but you have x squared plus y squared equals r squared, right? We know if our x and y values is like completely equal to this boundary, r squared, then it's going to be on the like edge of a circle, but now we're in 3 dimensions, so on the edge of a sphere. I don't know if it's an edge. I feel like that's a bad math term. Please don't hurt me. But yeah, if it's equal, we're going to be on the boundary of the sphere. If we're less than, we're going to be inside, and if we're greater, we're going to be outside the radius, right? Wish I had like a whiteboard on my screen, but basically, instead of using just like straight coordinates, maybe I can actually. I can do some MS Paint stuff. Sorry. Let me pull up MS Paint. Yeah, but instead of using like I don't know, we have some sphere. Instead of just using some point x, y, z, we're just gonna have some vector from our like camera do this, right? And this is gonna be like cx, dy, dz, right? And we're gonna do that minus this point, right? Instead, and that's pretty much the same thing because you know, our camera is usually located at the origin, right? So since it's located at the origin, it's just going to be minus x squared, which is the same thing as x squared. But the reason we're doing this is so we can get a quadratic equation to solve later. Oops. But yeah, and instead of doing, oh wait, no, sorry. But instead of just writing it like this, we're gonna write it as dot product, right? Because these are now vectors, right? Instead. And, we're going to have cx minus x, right? Times itself plus dy minus y squared, or times itself plus dz minus d squared, right? And, it's just the definition of the dot product. So now we have that. And this is starting to look more like a quadratic formula, which is nice because instead of having just p, right, which is kind of vague, we can replace this p with what array is, right? Because array and a point are kind of interchangeable, right? Because we can just find the t, which the t value along the array, which evaluates to that point we're looking at, right? So we're gonna replace this p with array, right? Ooh, voice crack. Yeah, we're gonna replace this p with array, and now we have this, and we're gonna just kind of just rearrange things around, and then we're gonna take the dot product again, and we get this right here. Feel free to look over the math to verify it if you're really curious, but we get this down here, and this is just the quadratic formula where d dot d is our a, negative 2d dot d minus q is our b, and d minus q dot d minus q minus r squared is our c. We're just going to solve this, right? We're going to implement this in the code, by the way. Once again, please take a look at the collab. But yeah, we have this, A, B, C, and we have some P. This is our quadratic formula. The way I was taught this is one sad boy couldn't decide whether or not to go to the radical party, so one square boy missed out on 4 awesome chicks, and the party ended at 2 a.m. Kind of funny, kind of silly, but we're going to solve for this t, and we can either get no t if the determinant is negative, we can get 1t, or we can get 2t's, right? And this directly relates to the geometry of the sphere as shown here. And this is how we implement it in the code. And it's basically just what we went over, right? So we have this ray, which is our origin, because our ray is point equals q plus the e, right? I forgot to mention what this d is, right? This d is our direction. It's also a vector. I don't know if I have an image. Like if we have one of these lines, it would be the direction, right? Because we want to scale up that direction. Yeah. So these are direction, and q is our origin. And so we're just going to do the math here, just in code instead, right? And we're going to find a discriminant. And like I said earlier, if the discriminant is negative, then we don't have anything, right? Otherwise, we have hit something, and for now, we're just going to return a t, right? A t value of like where we are along the ray. So later on, you can kind of implement some sort of detection system or like double check system to see like if you get like two t's, which one did you hit, or like which one is actually valid, right? Because obviously, even if you hit two t's, it doesn't really matter because you're only gonna print out the first one, the one that's in front, right? But sometimes the first t value doesn't really make any sense. Like it might be like negative, like behind the camera or something, right? So there later on in the book they do checks, if I recall correctly, about that t value. Now that we have this t value, we're just gonna return a color, right? This ray color function we have just has our linear interpolation from before, and also this hit sphere function we just coded, right? Sorry if I'm not like expanding on what the parameters are, but you can always pause the video and look at it if you want to. So yeah, we have this ray color formula which takes an array and returns some color. Python doesn't allow you to name a class anything other than like its initial name, but C++ does. So this would usually be like color3. But yeah, we have this sphere, and we're going to see if we hit it, right? What is this first one? This right here is where the sphere is in the world or scene. This is its radius, and this is just the ray that we're sending out, right? And if we hit it, we're just going to return some vector, some color, right? Here it would be green, right? Which is kind of funny because the next slide I'm pretty sure is a red sphere, right? Probably just an old picture. Yeah, but that's basically it. If we hit a sphere, we're going to return some color and hit a sphere, right? If not, we're just going to render out the background. And here's an updated version of our original output loop. We're just going to write it out as a file so we can save it. We're going to write out our image like resolution. By the way, there's like a little bit more code for like the vector class and image resolution, and it's in the collab, right? So we're going to do that, and then we're going to go through our scan lines, we're gonna find the pixel center, uh, which, like I said before, is just like kind of like that little eye of the center, where it's just like half this delta U. First, we're just gonna find like the top left corner, and then we're gonna add how many delta U's and delta V's we've iterated by, and we're probably just gonna find the like halfway point. Yeah, I'm pretty sure I coded delta U as like half of the delta U that's on the diagram. But yeah, and we're gonna find the direction of the ray, which is from wherever we're looking at to our camera center. That's the direction. And our ray itself, which starts at the camera and then goes in that direction. And then we're just gonna pass it into that function we did earlier. And we get this picture. Woo! Yeah, that's pretty much it for that part. But this is kind of like a boring image, obviously, right? Like, how do we get a better idea, like, perspective, right? Like obviously the ray on this right or this part of the sphere on this right side is further back than the center. We can get kind of an idea of that based on the normals, right? So we're just going to give each normal a different color for now, just like a basic visualization. This is not in the code, so you can look at this or read the book to see what it looks like. And it's basically, we have this hit sphere function we had from earlier. We're going to get the normal vector, which is basically just like where we are along on the ray, like where we hit the sphere, minus the sphere center, which is right here, x0, y0, be -1, so right in front of the camera at 0, 0, 0. Obviously, minus like the edge of the sphere, minus the center of the sphere, we're going to get normal that's just pointing straight out of the sphere, right? And then we're just going to return some color based on this. And we get this. And that's pretty much what I had planned to present for today. So yeah, if you want to look a little bit more deep into this, these are kind of like the next couple of chapters in the book. We have anti-aliasing, we have use in specular materials, glass, etc. Just to kind of explain what these are first. Anti-aliasing is smoothing. Like you can kind of see it already, like how the edges of this sphere are kind of pixelated. You can kind of see the jags, right? So like anti-aliasing basically just blends this in with like, I think the way they do it is like a pretty just simple averaging of like each pixel with its surrounding, right? So like we would blend this edge pixel with these like blues from the background, and it would make a smoother transition. Yeah. And the background itself would also be averaged with this like sharp edge, and it kind of just mellow out. So that's anti-aliasing. Diffuse materials are kind of like flat materials. So like we see these spheres here, right? If a ray hits the sphere, right? These rays don't just hit the sphere; they bounce around, right? Light bounces back off the sphere, right? So it's gonna bounce into one of these spheres, and diffuse is basically it's just gonna bounce equally in every direction once it hits the sphere, and that kind of like once that's like kind of an averaging of the color that comes off when it hits the sphere. And since everything's average, it kind of just makes things look mellow and flat. Specular materials are kind of like this metal ball where you have like this highlight here. Doesn't necessarily have to have a reflection. glass is glass, and pretty much it. So if you watched all the way through, thank you for watching. Don't forget to like and subscribe. Uh, yeah, thank you. Have a good one.